talk about the fundamentals of SCADA today. First, just to give you a little bit of history on me. I've been in this industry since 1980 or so, and basically I worked at 2 or 3 different companies. I've kind of worked up from the ground up, from building panels is kind of where I started, all the way up through engineering management, sales management, service management. Currently I work for a company called ICS Healy Ruff as one of their territory managers, and unfortunately this is not one of my territories. I'm actually all of the western United States and part of the east. But today we're going to talk about fundamentals of SCADA. And SCADA is a huge topic, as a lot of you know. And many of you will already know much of what we're presenting today. If you've got a SCADA system, or you know people that have SCADA systems, or have done some research, but hopefully you'll pick up a few things. And then kind of at the end, we're going to talk a little bit about where SCADA is going, some of the new technology that's out there right now that might be right for you, something for you to consider. So we're really going to talk just very fundamentally, and it's going to be even more like a shortened fundamental, like the fun of SCADA. So, pardon the pun, but so we're going to talk about just really kind of what SCADA is, sensors, controllers, traditional SCADA review, and then cloud-based SCADA. This is kind of the new thing on the block. And I'm going to just remove my finger so it doesn't keep crinkling on the microphone. But SCADA functions. Basically, what is SCADA providing? Mechanical electrical interface. Basically, what it's doing is it's monitoring your system physical parameters and presenting them in an electrical format that you can then manipulate and then take it back out into the field, and you can manipulate relays and things like that to turn things on or off and use other mechanical gear. It's going to gather system data over a local or a wide area network. It can use many different types of communications medium, sometimes only one, sometimes multiple types of communications medium. We'll talk a little bit about that. It should provide a user-friendly method for you to view this data. It shouldn't be so cryptic that it's very hard to understand. It's not like you're trying to read the programming language. It's brought out and made a lot more user-friendly. It provides a means to allow centralized or distributed control as well. Especially water people, you've got a lot of equipment that's geographically dispersed in an area. So you've got to, in order to control a well pump, it needs to know what that tank level is that may be miles away, or other types of data out there. The other thing is you've got lift stations too that are monitoring the status of those lift stations, and that data needs to come back so that you can know if there's a problem out there. Sometimes so you can override the control, those types of things. SCADA system is also an active monitoring system, and what that means is that it's continuously interrogating itself. It's always up, and when it's not up, it will detect that, and it will let you know that there's a problem out there. So you can go home at night knowing, okay, my system is running until it tells me that it's not running. Data storage, you can accumulate a lot of data. SCADA systems are gathering this data, and it's not just presenting it to you, for real time, what's happening right now, but this data is archived, and it's stored, it's used in reports, and it can also be used for, going back in time and kind of looking to see what was going on at that time, what were my flow rates at that time, what were my total flows. So all that data can be utilized, and then you can get creative as to how you want to use that data, how it could help you in the future. A lot of times consulting engineers like that kind of data too, to kind of see the growth of the city, what's going on, how fast are we going to need to update this station, when do we need to increase pumping capacity and things like that. It's also used for remote notification of alarms. So there's a lot of different ways. In the past, it used to basically be an alarm dialer that you would get, an alarm horn or alarm light. Now you're getting notified on your cellular phone. You're getting phone calls at home with voice messages that are telling you what's going on. You're getting emails sent to your PCs. Another important facet of SCADA that it brings to you is remote access and control. So you can be driving around in your trucks. You could be, even now with the internet, you could be on vacation somewhere in an exotic landscape, Hawaii or something, and you could get an alarm on your phone. And you could go to a laptop or even on your phone if it's a smartphone, and you can access your system. You can see what's going on. If you have the right access authority levels in your system, you can actually turn things on or off, and you can change your set points. So it's basically just being like you were sitting in front of your console back at the administration building or the plant or wherever you might have your main operator interface into the system. Another important benefit of SCADA is that it can bridge different technologies together. A lot of communities have got lots of different technologies out there. Maybe this was put in 1980, this was put in 1995 and 2005, and they're different technologies, and they can't really talk to each other, but a SCADA system, especially at the PC level, can provide gateway access from one technology to a different technology platform so that you can share that data basically seamlessly. So it gives you a lot of functionality that way. So main benefits of SCADA is going to save time and energy. It's going to give you complete system visibility out there, depending on how much of it that you're actually monitoring, but everything that's monitored you'll be able to see. It'll give you the logging of the data. It should provide improved asset management, and meaning that you'll know what your run times are, your number of starts. It can keep track of the calendar days that these things are in operation. It can provide work orders for you, things like that automatically to help you track things. Just like you might use a calendar, in the Microsoft Office world to remind you of things or keep track of things. SCADA systems will do the same thing with your equipment. The other thing is that it improves safety. So you're getting a notification that there's a problem, the station's overflowing or it's backing up, and it could start getting into homes and cause hazardous waste to get in there and cause other kinds of problems. When you hear about the alarm, you'll know what it is, when it occurred, so when you arrive at site, you'll basically be prepared for it. You can send the right people for those kinds of problems. And then active communications. Again, it's always checking, self-checking, making sure that it's working. So in summary, SCADA is really risk mitigation and increased operational efficiency. In the past, SCADA systems were very expensive. They still are kind of expensive, but they're not as expensive as they were. And the capabilities and functionality of these systems is going up, and the costs are either staying the same or even coming down, depending on things. And really, the technology, the hardware technology costs are coming down. Unfortunately, the labor costs have been going up, and that's been kind of offsetting a little bit. So now it's easier to justify the expenditure. Your cost isn't paid back in years. It's paid back in months in a lot of cases. So what are the components of SCADA? When you look at a SCADA system, a lot of people overlook the fact that your sensors are part of the SCADA system. And sensors tend to be some of the most important pieces to the SCADA system, but you've got your sensors, and then you've got your controllers or your telemetry devices, and you've got a communications media that's in there. And then often in a SCADA system, you've got a PC out there. A SCADA system doesn't necessarily need a PC, but in our industry, we typically associate a SCADA system as having a PC running some HMI graphical software somewhere with reports and things like that. Sensors, these are the devices that sense physical change out there. They take the physical world, convert it into an electrical signal that can be read by the SCADA system, the telemetry equipment, the controller, those kinds of things. So they will represent that information that's being monitored out there. And sensors can be analog or they can be discrete devices. A discrete device is basically a float switch that on and off, just like your switch for a light. If it's on, you flip the switch, it's a discrete signal, tells the light to turn on, turn it off the other way. The other signal is an analog signal, which is produced by a pressure transducer out there. The pressure transducer will give an output proportional to that pressure that's sensed. So a lot of you may have float switches that I just need to know when it gets to that level, I'm going to turn this off, or I'm going to provide a high level alarm, or I'm going to use it as a backup system. But the analog signal may be used to give you more precise control and more precise knowledge of exactly where that process is for your tank levels and things. And in a lot of applications, you need an analog signal in order to control things properly. If you're trying to do chemical feed rates and things like that, and maintain constant pressures, constant levels, constant flow rates, your processes within certain parameters, analog sensors are really needed to do that. So that's part of it. Some basic terminology, we talked about discretes, normally open, normally closed. People get a little bit confused once in a while when they talk about normally open or normally closed, but normally open is, and normally closed are what is the sensor doing in its natural state, and this is really associated with discrete sensors. So if your flow switch is hanging there, it's not affected by any water or anything in there, what is its contact doing? Then it would, if it were closed, it would be a normally closed. The analog, infinite variable, direct acting, the main difference there is it making contact with the process or is it not making contact with the process? A ultrasonic level sensor is not a direct acting sensor because it's not actually directly connected to the media like a submersible level transducer would be. Differential, output differential, a lot of times you're going to have two pressure transducers in there and it's going to measure this side, this side of the tank versus this side of the tank, or from the top to the bottom, or head loss in your filter systems. And all you're doing there with the differential is you're measuring what's the difference between pressure here and the difference from pressure here. And maybe it's only 1 psi, it might be 10 psi, even though the system may have 200 psi in it, but the difference from the top to the bottom is only 3 psi. Intrinsically safe, this is common for lift station applications or wastewater treatment plants where you could have explosive gases. Intrinsic safety isn't just unique to our industry, though. It's used anywhere where there might be something that's combustible or explosive, grain elevators, mines, things like that. They're used out there. There are specific divisions and classes that are used to determine what types of intrinsic safety that you need with our systems in the water and wastewater. But intrinsic safety, really basically what it does is it limits the amount of energy that can go to that sensor, so that I could take, if something were to happen and the wires became exposed either through friction or accidental cutting or something, or pulling it, if I were to touch those wires together, a lot of times you can take electrical wires and you get sparks and arcs. The intrinsic safety barrier will actually limit the amount of energy, so I can do that and I'll never get a spark or an arc or anything that could cause an explosive atmosphere in order to explode or ignite it. Loop powered, I'll say this simply is, it's also referred to as a two-wire device. This is where the device gets its power through the same wires that it's producing its signal output on. So I kind of look at it like a regulator. It's 24 volts DC going in, the device, and then the transducer is regulating the amount of current that is going out of it. So maybe 4 to 20 milliamp signal. 20 milliamps is at the highest range, 4 milliamps is at the lowest range. If it's somewhere in the middle, it's going to be 12 milliamps or so. So it just kind of regulates the amount of current going through it. Twisted shielded wire pairs, these are important to use on your analog sensors. What they do is they protect those wires from induced electrical noise and voltages that can come into your system. Also help protect from transients that might occur. When you're turning on and off electrical loads in your system, whether it be a plant, lift station, well site, there's electromagnetic radiation that emanates from anything where power is being produced. The wires going through produce electromagnetic radiation, the motor producing electromagnetic radiation, and that electromagnetic radiation will cut into those signal wires and induce a voltage, which then could throw off your actual reading of the system. So twisted shielded wire pairs actually provide quite a bit of isolation and help, but they're only effective if they're grounded. They have to be grounded properly, and you can only ground them at one end. And a lot of times if you're having problems with your analog signals out there, it's because they aren't shielded properly or they may not be grounded properly. Sometimes you see them grounded at two ends, and that causes what they call a ground loop. And that allows current to flow from one ground point to the next ground point, because no ground point is the same. If I were to take two ground rods right now, stab one into the ground where I'm sitting, stab one into the ground where you're sitting, there's going to be a voltage potential between you and me right now that's going to want to cause current to flow. When current flows, what does it produce? Electromagnetic radiation. That electromagnetic signal will cut into those wires and again cause a problem. So that's why ground loops are not very helpful. The other thing in a SCADA system is you got controllers or PLCs that are out there. PLCs are more common in our industry now than they ever were. Basically everything, almost everything is a PLC that you might have in your panel. PLCs are simply programmable logic controllers. And they come in all sorts of forms, fashions, and different levels of capability with them. And some of them are actually built for certain types of applications, but most of them are really for a generic application that are used by many different industries for many different functions. are out there. The controllers can be intelligent or they can be non-intelligent. Non-intelligent typically means it's not programmable. You might be able to configure a few things on it by moving some jumper pins around and selector switches and things like that, but it's really not programmable. The intelligent ones are programmed. They can be for a generic or an application-specific type system. So you may see a PLC out there that was actually developed from the ground up to be a lift station controller, or maybe a filter controller or something like that. But most of them that you're going to run into are going to be generic type PLCs that were adapted to your application. Some terminology: PLCs, OI. Most PLCs don't have an operator interface built into them. They need another panel there that's connected to the PLC that can actually be kind of the window into the system. The operator interface is typically not the controller. The PLC is the controller. The operator interface is simply a window into it. And you have to create a communications network between the PLC and the operator interface in order to share and see that data and bring that in. To program PLCs, you're typically using ladder logic. I'm sure you've all heard of ladder logic. It's pretty commonly used. And most PLCs also have the capability to be programmed in a function block. And ladder logic, if I were to take let's just say a 4-stage alternator with first on, first off capability, pump fail replace logic built into it, it would take me 273 ladder logic programming elements to do that. So as you're looking at this logic, you're going to see rungs and rungs and rungs and rungs of data or logic in there that represents that specific function. I can actually pack all of that into what they call a function block. So now instead of all these rungs of data, there's one block in there with some links connected to it. It just makes it a lot easier. You can build a lot of functionality into it. You can cut the programming costs down and actually give you more functionality, and it's a lot easier to troubleshoot later on in the future. So you'll use that. And then isolation. You'll see isolation used a lot in SCADA systems, and basically what isolation does is it typically refers to an electrical isolation because of the noise and the transients and the ground loops that can occur out there. You like to have isolation on your inputs into your PLC systems or your SCADA systems, just to make sure that you're not getting erroneous, high-level electrical spikes coming into it, or even sometimes surges that can come in there and damage those inputs. Telemetry. Telemetry is simply used to transfer data between remote devices. Now, I'm actually doing telemetry right now in several ways. I'm speaking, the mic is picking it up, converting it to an electronic signal. It's being broadcast out to a receiving device that's reinterpreting it and then putting it out through the speakers. That's really what's going on in the SCADA system as well. It's taking information, transmitting it, and then making it available for other viewing or other uses out there. Telemetry systems permit remote monitoring control out there. You've got telemetry in your plants. You've got, most of you, if you have a new car now built in the last 10 years, you've got telemetry in your car. It's monitoring your sensors. You've got a computer in there, and that's all being done via telemetry as well. So it doesn't have to have big Yagi antennas hanging out of it. This little controller is controlling my laptop by telemetry right now. So what does a typical telemetry system look like? Well, you've got geographically dispersed equipment out there. This one just happens to be a radio telemetry system, so you're going to have a radio antenna at the different remote sites that are out there. All that data is going to be coming back to a central control panel. You may have an operator interface there that actually is configured and programmed to represent that water or wastewater system, whatever you're monitoring there. Some telemetry terminology: remote telemetry unit. So basically what this is just a telemetry unit that's remote from the master location. The MTU and CTU, master or central telemetry unit. This is the main unit that may actually control all the communications in the system. Maybe the main viewing point in that system. The ITUs, the intermediate telemetry unit, that may be a repeater site that's out there. So because of limitations and communications and the fact that some of your stuff may be very widely distributed out there geographically, you may need multiple sites in order to communicate from one to get to that end site. And you'll use an intermediate telemetry unit to do that. Submasters, often this is a technique that's used out there where you're trying to improve system scan time and performance, or possibly you're using that kind of like an intermediate telemetry unit, but it's on its own communications channel and it's pulling its own RTUs, and then it is being pulled by a main master at another location. So it'll concentrate all that data in its zone, and then it'll be pulled by the main master, and all that data will go up to the main master. And you can cut down your scan times and improve system performance that way. Open architecture, often you're going to hear this in SCADA systems, well, we're open architecture. Well, there's a lot of differences as to what really is open architecture. In the SCADA world, open architecture exists on two planes. It exists in the programming world, and it exists in the communications world. When you're doing programming, what that means is that the software is available. You can buy it, or you can get it. You can program it yourself, or you can give it to somebody else and they can program it. It's not proprietary. It's not something you've got to run out there and buy a license for and maintain this kind of software. It's true open architecture. You can just go buy it, just like you go buy a light bulb right now. Go to the grocery store, you buy the light bulb. Put it in, no problem. If that were a proprietary light bulb socket, then you may have to go to a specialized proprietary provider of light bulb distribution centers or things like that. The other thing is in the communications world. In communications, open architecture means that I am communicating using a protocol that is an open, published standard. I don't have to go to the manufacturer or developer of that protocol and buy a license to use that communications architecture or a development kit from them to be able to develop a driver or something like that so I can now communicate. So when you're evaluating PLCs and communications and things like that, we tend to try to go open architecture is what our recommendations are, things like that. Addresses are used in communications because I'm broadcasting on radio, and if everybody thought they were all, RTU number one, they'd all report back. So we use addressing in the communication stream that provides a unique identifier for each site out there. And incidentally, that's what you're doing when you're going out on the internet. Every website that's out there has a unique address, URL associated with it, so that you're only getting to the right one, and that one's only responding. Bits per second, BPS, just transfer of data. You get error checking pretty much at all levels of your PLC and SCADA systems. A node, this is commonly used when you're looking at PCs. You may have administration networks in your buildings right now. You may have 3 or 4 computers. Each one of those computers represents a node, and that's typical terminology for a PC type system. When you get into the radio systems, you got other terminology there. You got the FCC, Federal Communications Commission. If you're using licensed frequencies, or even if you're not using a licensed frequency, the FCC is still going to be involved some way, either telling radio manufacturers how much power they can transmit, how wide their bandwidths can be, and things like that. Line of sight is commonly used. Line of sight just simply means what it says. The antenna, the top part of the antenna, wherever the radio signal is emanating, needs to be able to see the other top part of the antenna that's at the other site. Some frequencies, the higher frequencies, typically need more line of sight. And when we say more line of sight, well, what is this? Either line of sight or not line of sight. But you'll hear the term near line of sight too. So for me, I can see the top of that tower over there right now, no problem. If there's a building, a church over there that's a little bit harder to see, there's some trees in the way, that would be kind of near line of sight right now. So gain, that just simply says I'm focusing the energy on my radio system, my antenna. My antenna is constructed uniquely so that the energy that's emanating from it isn't going out in all directions, everywhere equally. That would be more like an omni antenna, but you could do that. But with the gain, what it does is antennas is it focuses that energy. And if I can cut that radiation pattern down in half, I double my gain out to the area that I'm really trying to focus that energy to. So and every time you have a 3 dB gain on your antenna, you're doubling your energy out there. Loss, this happens in radio systems, this happens everywhere. Only about 80% of the electrical energy that's made in a power plant actually gets to your home. The other 20% is lost in transmission or other connections or heat energy from going from transformer to transformer to transformer. Wherever you have heat, you have loss. Even though these wires are running out there, they're actually producing heat because they're conducting electrical energy. Atoms are being pushed through that wire and it's causing friction, causes heat, causes loss. Different types of antennas, Yagi, used typically for very directional applications out at your RTU sites. The Omni may be used at your main site because it needs to be able to communicate to a whole bunch of different sites out there that have different azimuths and different locations. ERP, effective radiated power. This is basically what's the effective radiated power of your system. FCC will limit the effective radiated power as a function of power output of the radio, gain of your antenna, loss that could occur with the coax cable, the connectors and things that you have. So going forward, as part of repeating functionality, duty cycle is just the amount of time that the radio is actually transmitting. The master probably will have a 50% duty cycle. If I've got an RTU, a radio out there that's part of the 10 RTU system, that RTU may only have a duty cycle of 10% or less. Licensed radio, you have to go through the FCC and get an actual license on it, but it's your frequency to use and it's dedicated to your application. Unlicensed radio, the FCC has set up a group of frequencies out there that is uncontrolled. Anybody can use it as long as you're using radios that are compliant with that band out there, but you have no restrictions. A lot of times people want to use spread spectrum radios. Those are unlicensed radios. They say, well, they're interference free and things like that, but they're really not interference free. They do, in metropolitan areas, you can get a lot of use of these frequencies because everybody can use them. Your home security systems, your baby monitors, most of your computer networks that are wireless at home will use those frequencies. So you get a lot of people using them. And they don't always make for the most reliable system for water and wastewater because of the geography that you have out there and how spread out things are. Frequency hopping is used by spread spectrum radios. This technology has been around since World War II. It's how our military kept the enemy from capturing our transmissions and things like that. So it's been around. It's not new, very tried and true. Some components of telemetry. You got an idle mechanism. This is built into the controller. It converts that output from the sensor into a low-level electrical signal that's monitored by the processor. The processor is what takes that data, matches it up. It'll have a modem on it. The modem, basically what that does is that takes that electrical signal and converts it to something that can be used on the media that you're using, whether it be a radio, a phone line, a pair of wires, whatever. The communications medium, this is actually the network that you're communicating on, whether it be wires, radio, cellular, satellite radio, things like that. And you can have multiple communications media used simultaneously in your SCADA system. Protocols. Protocols are used to format the data that's out there. I kind of liken them to languages. You have to be able to communicate. Each device has to utilize the same protocol in order to communicate. I'm up here speaking in English, but if some of you were German and could not speak English at all, you and I would not be able to communicate to each other. You'd need some kind of translator, gateway, or you need to learn English. But it also provides, some error detection and gets your data through. Traditionally, SCADA is going to, you've got your telemetry system that we talked about with that master telemetry unit there, but now we're going to add a computer in there. So the computer would then connect to the master telemetry unit and it would display the data in maybe a larger graphical format, then you get your reporting and things like that. You may have some remote access through a laptop or an intelligent portable device that you may have, an iPhone or an iPad or like that. With President SCADA, traditional, you purchase it, you maintain it. So you're responsible for the server and any PCs that are connected to it. All the software that's on the computer, anything that requires licenses, you have to maintain. Your annual license fees, if there's maintenance contracts, all of that has to be picked up. You're responsible for your data integrity. So I mean, it's your system. It's just like your computer at home. If you're having problems with it and you need somebody to come in and fix it, you know, nobody else is responsible for the data other than you. You have to bring people in and get that taken care of. System security, you're responsible for that. You keep your doors locked, or you keep a firewall on there if you have remote access and things like that. You're the maintainer of your access codes into the system, so all of that is your responsibility. You may need some IT integration in there too, so if for a complicated SCADA system, you've got a lot of networking going on, you may actually have to employ the services of an IT person to help that out. Then, that equipment is probably going to need to be upgraded every 4 to 7 years or so. Sometimes if you can go longer, and some groups actually end up going shorter. But you're going to be probably looking at some kind of an upgrade, and that upgrade is going to consist of hardware and upgrades in your software. Many of you probably have already gone through upgrades, and you're almost paying as much for that upgrade as you did for the original system. So there's quite a bit of cost that can go along with it. So you're kind of feeling the pressure about SCADA systems. You know, can we afford it? Because they're expensive. Can we maintain it? Because they're complex. And then how do we make sure that we get the most out of the money that we have and that investment? So because things are so rapidly evolving, you know, it's just like anything. You jump in and then 3 months later there's something new out there. It might be better, it might be cheaper, whatever. But you just kind of have to jump in at some point and hope that, you know, you've made some good picks at that point. So one of the things that we're kind of promoting right now, it's kind of evolving, is cloud-based SCADA. This is, you've heard of cloud-based information. Basically, you're going out on the network, you're finding a server somewhere, there may be some application software there or things like that, where all of that resides on a server that you don't own, that you don't maintain, that you really didn't pay for. You're getting kind of free stuff out of it. So, but with cloud-based SCADA, you don't have to buy the hardware, you don't have to buy the software, you don't have to maintain the system. So that can take a lot of cost out of these systems, a lot of worries, and a lot of complexity. So the cloud was recognized back in 2011, 2012. One of the main things here is that the cloud can reduce SCADA costs by up to 90%. So I can reduce my food costs by up to 90% too. But getting to actually 90% would be a little bit tough. But it's certainly 50% or 60, even 70% is certainly possible. Control engineering has listed many other things about cloud computing on it. Basically, they're saying it's going to get increased availability and it could be more reliable because you're adding things to your system. They can be incrementally added. You're not paying to have a big system out there for a lot of future growth because the cloud-based system can actually grow and you're not having to pay for any additional tag names or anything like that. It just kind of can grow with you. So some of the terms, cloud computing. Computing resources, hardware and software that are derived as a service over a network, typically the internet. But cloud kind of gets this thing because everybody represents that by a cloud, and that's really how it kind of got its term cloud computing, not from a technical thing, just how it's being, the icons, the images that are used for it. Your URL, which is, whenever you're going to a website out there, you've got a unique address, and that's what the URL, Uniform Resource Locator. The internet is worldwide, and the intranet is company-wide. Sometimes there's confusion. I'm on the intranet or I'm on the internet, so you have to kind of listen a little bit. So many of you who have many computer systems networked, for your city, you probably have an intranet in your system. And whenever you go outside of your system or your building or possibly anybody that has the intranet set up, you're going actually to the internet out there. So cloud-based can eliminate a lot of headaches. You can get all the same functionality as a traditional SCADA system, graphics, reports, everything that goes along with those, and now they can be done over the internet. Some additional things with cloud is, one, you get full redundancy. Typically, these cloud-based systems are set up by somebody out there. They have multiple servers that are already backing themselves up. In our case, we have 2 servers set up in a server farm location that's set up for this kind of stuff. The building's very secure, multiple power systems coming in, communication systems coming in, environmentally controlled to optimize, the longevity of the equipment. All of that is there, and we also have redundancy back at our building in case that fails, and then one of our owners has some redundancy built up at his house too. So there's 3 levels of redundancy. It's geographically dispersed, so if something were to happen even to that building, and the building in Minneapolis blew up, the backup system at our factory would pick up. And if something happened there and that couldn't pick up, then the owner's servers could actually be put online within 4 hours, so there's quite a bit of security that way. The physical security that comes with these systems too. The building that these servers are located in, there's armed guard at the front door. You can't get in there unless you have authorization to do that. So somebody just can't walk in, start unplugging things, connect up to your computers and start grabbing data and things like that. In a wastewater treatment plant or water treatment plant, often the doors are left unlocked. People could actually go in there and start looking around and things. So you get better physical security. The cyber security, because this is a server farm and they have all their firewalls, they monitor it all the time. And if there's anybody coming in, any malicious attempts to get in and disrupt the network or the system, it's detected quickly and it can be isolated, and we are actually notified right away that there's a problem. That's not something you typically would get in a traditional type SCADA system if you own the computer and had all that responsibility. So we can react to the threat quickly and mitigate it and take care of it. Data and program backups are all in there because of the redundancy. Unlimited tags and user licenses. Just like you're going out to do shopping on the internet. You go to Target. Well, there's tens of thousands of people accessing that Target website right now. Same thing can happen with your cloud-based SCADA system. So you don't have to buy a user license for each person that's going to access this. They just have to know the passwords and the usernames in order to get into the system. Scalability, the cloud-based SCADA systems, hundreds of thousands of tag points, a lot more than you're ever going to need are available, and again, lots of different users. Automatically, the software is automatically updated. You're not being notified, hey, you got to give us some money because we need to update the software that you're using out there. Cloud-based systems, the manufacturers are already updating this software, so you're always kept current. It's always moving forward. You'll never have an upgrade cost again with it. The communications and system connectivity are all managed. When you're looking at how do I connect to the internet right now, well, you're going to have a cellular carrier, or you're going to have your broadband carrier, maybe it's a hardwire connection through your cable company or your phone company, and all that communications architecture is maintained by somebody else, and that's part of the cloud system. So how does it work? Here you've got your remote sites and multiple customers out here. Customer A could be looking at his lift stations. Customer B may have a water system. Customer C may have a plant out there. And this could all be the same customer, or it could be separate customers out there. It connects to the main servers at the secure data center through a VPN, virtual private network. And a lot of you, if you have intranets in your building right now, you're probably using virtual private networks to gain access to those systems and get the data. On the other side, the data comes out to you as to view it, and it could be set up so that only customer A can see customer A data. Customer B could only see customer B, customer C could only see customer C. Or you could set up where customer A can see everything, or customer B can see everything. So it gives you some flexibility that way. And for that communication, you're using an SSL, secure socket layer. That's the same technology that banks use right now for when you're doing banking transactions online. You can tell that you're using a secure socket layer anytime that you're on the internet, and it's got the HTTP and then an S on it. And that means that it's a secure connection, and it's using the secure socket layer in order to do that. So very, very secure that way. Some terms, internet service provider, provides access to the internet. Most of you probably know that. VPN, virtual private network. It's a private network that uses a public network. So yes, you're going out on the internet. Everybody else is out on the internet. but it creates a tunnel, basically, a tunnel that isolates you and your data from anybody else being able to hack into it, look at it, see it, so it keeps security that way. The secure socket layer, it provides a little bit of additional security in it. It's utilized for accessing different types of functionality that you might have when you're trying to go from one computer into another web server somewhere else. Wide area network. This is often you'll hear this in telemetry and SCADA. Wide area networks are like in a water system. I've got a tank over here, I've got a well over there, a booster station here, and a plant over there. I'm going to use a wide area network in order to communicate all those things. So I've got to have a communications media that supports long distance and things like that. So it could be lots of different things, radio, even fiber optics, getting information to your home through the phone lines is basically wide area networking. Local area networking, and as if we were all inside the same building. I'll use maybe an Ethernet communications network, which is a high-speed network that's commonly used for connecting multiple PCs or devices in there. It doesn't have to be a PC, it can be PLCs. Your controllers could be networked. Your operator interface could be networked. So what do you get with the iControl or the iCloud? You get, remote accessibility, you get the full SCADA, you get the process control, asset management, data reporting, monitoring, alarming. So the cloud-based SCADA is just what you're getting with the traditional SCADA system. Your system overview can look like this. So these are your sites. The red boxes mean that that station is an alarm. You may want to take a look at it, see what's going on there. So you get your graphics, you get your data presented to you, just like you're used to seeing it in a traditional SCADA system. You can pull up additional boxes to set points, turn pumps on or off, set your mode of operation. You have trending functionality. All of this data actually does stay on the cloud-based system for over 2 years. So that data is out there, and you can download it to your laptop and run it into an Excel spreadsheet, save it to disk for permanent storage. After your time runs out and we're going to start overwriting the data, it gets taken off the system, we will notify you, and then you have the option of us putting it on a disk and sending it to you, or just say, we don't need our data for any longer than 2 years anyway, so just let it go. Yes, sir? 2 minutes? Okay. I'm just on 4. I'm just kidding. We're almost there. Plant process overview. Again, just another geographical way to kind of look at your processes. So how does it compare? When we start taking a look at it, the traditional SCADA is actually going to have a higher cost of implementation because you've got more hardware to buy, more application software to buy, and those things. You're also, with the cloud SCADA, you got less software to buy, of course. So it's lower cost to initially put the system in with cloud-based SCADA, and then as you move down the timeline here, 3 or 4 years, you're going to have an upgrade cost that's going to have to go with it. So that kind of jumps up, and that's kind of how it works that way. So here's an example of a small system. 1 workstation, 2 remote access licenses, reports, alarm notification, 1 elevator tank, 3 wells, and booster station. It's typically going to have about 70 or 80 hard I/O points in the system. So when I take a traditional SCADA system, my initial cost is going to be about $37,000. If I want to add redundancy, that's going to cost up to $50,000. So I have 2 computers set up in redundant fashion. 1 fails, the other one takes over. I feel more secure that way. When I take it out 15 years, the life cycle cost of the traditional SCADA system is going to be $67,000 or $96,000 if I have redundancy. And so I'm looking at $838 per I/O point after 15 years, or redundancy is $1,196 per I/O point. I go to this cloud-based SCADA system, my initial cost is $18,000, about half. My 15-year cost is $39,000. Now what gets added into that is there is typically a cost for cloud-based SCADA systems. There's going to be a user fee basically for it, and that user fee is typically based on how much data is coming through and that, but you can still see that it's going to be a lot less than what you would get with a traditional SCADA system. So after 15 years, it's $39,000 rather than $50. And 15-year life cycle is $487 per I/O point, half of it. And redundancy is included. So if you want redundancy, and that was going to be part of your traditional SCADA system, then you're way ahead of the game. Collection system, 1 workstation, 2 remote access licenses. Got 2 minutes to move on. Reports, remote alarm notification, about 160 hard I/O points. Now I'm up to 54,000, add redundancy 67, life cycle cost, we'll just go 545 per I/O here, 725 if I have redundancy. The cloud system, again, is about half of that. And again, redundancy is included. Wastewater treatment plant, maybe a lot more I/O, 300 hard I/O points in there. Initial system cost is going to be 83,000. 15-year cost is 129, 430 per I/O point. They get to the cloud-based data system, and it really drops down here as far as life cycle cost per I/O point, $290 per I/O point. So, to me, it's very clear. This is kind of the way things are going. We've got a lot of customers out there that maybe wonder where it was specified, SciTech, Planscape, other types of HMI software with traditional SCADA systems. They see this, the consulting engineers are excited about it. They typically make that choice because, first of all, they get great cost savings. 2, the systems are very reliable, very robust right now. And anyway, that's kind of it. Questions? Yes, sir.
How important is security? And I've heard that there are a lot of systems that can be hijacked. So please, could you explain that and elaborate on that a little bit?
Yeah, the question is how strong is the security on these systems? That there's been a lot of people that have been able to hack into other people's SCADA systems. You heard about StuteNet that hacked into the Siemens WinCC software packages over in, I think it was Iran or whatever, trying to cause those kinds of problems. Anytime you're out on the internet, there is risk. But the risk is minimized by the fact that you're using virtual private networks and the secure socket layer out there. So from a cyber type security level, it's very strong. Your typical hacker is not going to try to waste any time going into a water wastewater system. And it's going to be very difficult for them anyway, because again, you got virtual private networks and secure socket layers out there that are actually protecting it. They're going to go for the money. So first of all, you're not going to be very attractive to somebody who's got the technical skills to go in there and try to do that kind of stuff. They're going to go to the banks and they're going to try to take the money away. But if you did have somebody who's really motivated to go in there and take your system down, it's going to be very hard for them to do that. And again, the cloud-based system is monitored for cyber attacks and malicious attacks. So if you want a SCADA system and you put your own system out there and you have your own remote access, the most secure way is don't have any remote access, don't have any networking capability on it. But if you do, and you need that, and most people want that because that's part of the reason for getting a SCADA system, the cloud-based SCADA systems are going to be a lot more secure, typically because they're monitored, they're continuously updated out there, plus there's redundancy and multiple backups. So if somebody came into one site, took stuff out of it or did things, the other site probably is not affected because it's linked differently from a backup standpoint. Does that kind of answer your question?
Alrighty. To stay on time here, we're going to, if you do have further questions, Troy will be in the back here in a couple minutes, but we need to keep moving with the Naeem's up next. But let's give Troy a round of applause.